So the question was like how does this step, how does this calculation of breakaway break-in point, like translate to the construction, final construction of the root locus in the sequence of steps that we are doing. Okay, we are going to look at that. Okay, so let's complete all the steps, then we will put everything together. Okay, yeah. Why we are making the derivative 0? Because of this, right? So when at a breakaway or break-in point, right, what's going to happen? Two branches of the root locus are going to intersect, right? So that means that the corresponding closed loop characteristic equation would have a repeating root for that particular value of k. Okay, because when two branches intersect, each branch represents one closed loop pole, right? So you are going to have a common repeating root, right, at that point. Okay, when you have a common repeating root for a polynomial, a repeating root with a multiplicity greater than 1, you are assured that the first derivative is going to be 0, right? That's why I did this aside, right? So that's why we are differentiating the closed loop characteristic equation or closed loop characteristic polynomial to be more accurate. Okay.
That would be the two different. Is it graphically got that way, or is it?
That's the definition of a breakaway point, right, and a break-in point, right? So I just illustrated it to you graphically. So there may be breakaway points, there may not be, okay, but this is the process to check. If there were breakaway or break-in points, they would imply that you have a repeating closed loop pole. That's why you are checking. See, we do not know a priori whether a given open loop transfer function would result in a breakaway break-in point always, right? It may not. Okay, that's why we are following this general process where we differentiate the closed loop characteristic polynomial, which is 1 plus k a by s by b by s, a of s by b of s, and then like we process it, right? So we get this equation and we check the values of k, right? Okay.
For some value of s, that k is positive, but it is just the root of the differential equation and not the root of the original.
No, it will be. Okay, we are assured of that. Okay, so maybe for those who are interested, I will give you a reference where you can go and look at the general proof and so on, right? Yeah. So we are not proving the results, we are only taking the results directly. Okay, I am only giving an intuitive understanding, right, to essentially understand each intuitive explanation, right, to understand each of these steps. Yeah.
So the whole step 4 is to actually check if there is a breakaway or break-in point, because it's not a general property of root locus.
You may have, you may not have, need not be there.
Only when we have multiple repeating closed loop poles, then we have.
Please remember, your closed loop poles are going to vary depending on the value of k, right? You are essentially figuring out, is there a value of k between 0 and infinity where I have a repeating closed loop pole? You can interpret this step in that manner. Okay, so that's an exercise which we are doing, right? From another perspective, that's correct. So the question that we are in a sense answering through this step is that, can I find a value of k if it exists where I can have repeating closed loop poles, right, for the given system, right? That's what we are doing. Okay. Yeah. So yeah, for the given open loop transfer function, if I scroll up, so please remember that g of s times h of s was k divided by s plus 4 times s minus 1, right? That's our open loop transfer function, right? So what are a of s and b of s here, right? A of s becomes 1, right? Because we want to write the open loop transfer function as k times a of s divided by b of s. So a of s becomes 1. What about b of s? It becomes s plus 4 times s minus 1, right? So please remember that. Okay, so let's scroll down. So a of s becomes 1 and b of s becomes s plus 4 times s minus 1, right? So this implies that a prime s is going to be 0 and b prime s is going to be 2s plus 3, alright? That's what we are going to have. So immediately if you evaluate this equation, so this would imply that a prime s b of s minus b prime s a of s equals 0. This would be essentially 2s minus of 2s plus 3 being equal to 0, right? That's what we would end up with. So consequently, a potential breakaway point is minus 1.5. Okay. So, once again in this particular example, the potential breakaway point turns out to be the same as the point of intersection of the asymptote. Need not be in general. Okay. Please, what to say, do not think that, oh, okay, all breakaway points or break-in points should be the same as the point of intersection of the asymptotes. This is a specific example, okay, where it just happens to be the same, okay, as that of the point of intersection of the asymptotes. But we are not yet done, right? So, we need to check the value of k, right, at S equals SB, okay, that is going to be minus of B of S divided by A of S, right, at S equals SB. So, we need to evaluate minus of SB plus 4 times SB minus 1 divided by 1, right. So, what do you get when you substitute minus 1.5 for SB? You will get, so 4 minus 1.5 is going to be 2.5, right, that is going to be in the first bracket, and then like minus 1.5 minus 1.5 is going to be minus 2.5. What is 2.5 times 2.5? 6.25, but there is a minus sign and minus sign which cancels off, it becomes plus, okay, you get 6.25 which is greater than 0, right. So, consequently this lies on the root locus. So, this is a breakaway point for the system that we are studying, okay, because the corresponding value of k is positive, right, that is what we could figure out. Yes, please.
How do we determine this a breakaway point and not a
Why not? Why did I say this is a breakaway point? Because you see that in this particular example there are two branches which are coming towards each other, because I know that minus 4 and 1 are two open loop poles, right. So, I know that each branch of the root locus is going to start from an open loop pole, they are going to come towards each other and then they are going to break away, right, would they not?
If we find out that the value of t is negative, then we can conclude that there is no breakaway.
No breakaway point, exactly. So, yes, so if the value of k happened to be negative in this particular case, right, so you could have concluded that minus 1.5 is not a breakaway or break-in point, okay. So, that is what you conclude. Fine. So, that is the fourth step, okay. Fine. So, let us go to the fifth step, right. So, we have done what to say, construction of asymptotes and construction of and calculation of breakaway break-in points, right. Those are the two new steps that we have done today, right. Let us go to the fifth step, right. So, what is the fifth step? We have to locate what is called as the angle of departure or angle of arrival. So, let me read it once again, and then we will figure out what it means. So, locate the angle of departure from an open loop complex pole, okay, that is how you should read it, or locate the angle of arrival at an open loop complex 0, okay. So, what does this mean, right? So, what does step 6 mean really? So, let's look at step 6. So, suppose if I had a scenario like this, okay, in this example which we are considering we do not have that scenario, but let us say, you know, like we had a scenario where I had two open loop poles like this, okay. So, I know that from each open loop pole I am going to have one branch of the root locus starting as k increases from 0. So, I will have one branch starting from this open loop pole and another branch starting from this open loop pole. Now, the question is then, along which direction will this open loop pole start? Okay, that is the question, right. See, in which direction it will go? See, when we had a non-repeating pole on the real axis, we argued that it has to be only on the real axis. Why? Because I can't go to the complex plane that is outside the real axis because I do not have a conjugate, you remember. But when my open loop pole itself is a complex conjugate pole to begin with, I can have the root locus branch going in any direction. How do I determine that? Right, that is the question we are asking ourselves, right. And the angle which it starts initially as it leaves the open loop pole is what is called as the angle of departure, right. So, I hope it is clear why it is called as the angle of departure, right. So, why do we call this angle as angle of departure from an open loop complex open loop pole? Is it clear why it is called angle of departure? Because I have a branch departing from an open loop pole, right. The question is that what angle does it make? Similarly, if I have an an open loop 0 which is complex conjugate, same logic, right. I have the real and the imaginary axis in the S plane. So, let us say I had two open loop zeros which are complex conjugates here, right. I know that we are going to have two branches coming in to this open loop 0 as k tends to infinity, right, correct. Now, the question is that like at what angle does it arrive at this open loop 0, okay. That is why it is called as an angle of arrival at a complex open loop 0, okay. That is the reason it is called angle of arrival, okay. Now, the question becomes, how do we calculate this angle of departure and angle of arrival. But before this, step 6 applies only when we have complex open loop poles or open loop zeros, right. Okay. So, otherwise step 6 does not even apply, right, because the example that we are doing, please remember what were the open loop poles and open loop zeros, right. See, for us, if you scroll up, the open loop poles were -4 and 1, open loop zeros were none, right. So, we only had real numbers as open loop poles, right. So, step 6 does not even apply for this particular example. But suppose if you had a complex conjugate open loop pole or open loop 0 pair, right, what do we do, right? How do we calculate the angle of departure and angle of arrival, okay? So, that is what we are going to learn. Is it clear what is meant by angle of departure and angle of arrival, okay? So, with this understanding, we will go to this step and then read through it, okay? The angle of departure from an open loop complex pole is going to be 180 degrees minus sum of the angles made by the vectors from the other open loop poles to this pole, okay, plus sum of the angles made by the vectors from open loop zeros to this pole, okay. That is the equation for calculating the angle of departure, right. So, how do we get this formula, right? So, let me take an example, okay. I am going to lead you to this answer, okay. I will leave you with a small exercise to do before the next class. Let us say, like I have a case where I have 3 open loop poles and 1 open loop 0, right. So, let us say that one open loop pole minus P1 is here, okay, and let us say minus P2 and minus P3 are complex conjugate open loop poles, and let us say minus Z1 which is the 0 is a real 0, right. Now, I need to figure out the angle of departure from this let us say open loop pole minus P2, right. So, we want to figure out the angle of departure from minus P2, okay. How do we do this, okay? For this, let us take a test point which is very, very close to ST. Now, what is the angle condition? G of ST, H of ST should be equal to plus or minus 180 degrees times 2k plus 1, right, k being 0, 1, 2, etc., right. So, that means that angle of k plus angle of st plus z1 minus angle of st plus p1 plus angle of st plus p2 plus angle of st plus p3 should be plus or minus 180 degrees times 2k plus 1, right. Do you agree? This is something which we have already done, okay. I am not doing anything new here. So, this guy is already 0, right, because we are considering k to be positive, right, the phase of k is already 0. Now, what is angle of st plus z1? Angle of st plus z1 is going to be the angle made by this vector, right, from the open loop 0 to this test point, which is very, very close to the pole minus p2. What is angle of st plus p1? It is the angle made by the vector drawn from minus p1 to st. What is angle of st plus p2? It is this vector. What is angle of st plus p3? It is angle made by this vector, okay. So, immediately we can see that this angle of st plus p2 is the departure angle, alright, because st plus p2, that is the direction in which the root locus will start, okay. So, that is the departure angle, and please note that as st tends to minus p2, because like st is like very close to minus p2, you can see that all the other angles become like this, right. St plus p1 can be approximated as minus p2 plus p1. What is minus p2 plus p1? It is the angle made by the vector drawn from minus p1 to minus p2. Do you agree? So, from here what I will get is that the theta departure from minus p2, which is what we are interested in, okay, is going to be equal to 180 degrees, right, plus the angle of minus p2 plus z1 minus, because I am just taking this to the right hand side, bringing this to the left hand side, okay, that is what we have done, plus the angle made between minus p1 and minus p2, the vector from minus p1 and minus to minus p2, and the angle made by the vector from minus p3 to minus p2, okay, and that is what this formula is, right. So, the angle of departure from an open loop, complex open loop pole is going to be 180 degrees, okay. Of course, this becomes plus or minus 180 degrees times 2k plus 1, I just take the positive 180 degree with k equals 0, that is it. You can take even the other way around, that doesn't matter at all, right. So, I just take 180 degrees plus this is the angle made by the open loop 0 with the corresponding open loop pole, right, the vector drawn from minus z1 to minus p2, right. So, that is what this is, and what are these two angles? These are the two vectors drawn from the remaining open loop poles minus p1 and minus p3 to the pole in question, which is minus p2, okay. So, that is what this step is, okay. So, with this understanding, let us go and read this step and we will stop there. The angle of departure from an open loop complex pole is 180 degrees minus sum of the angles made by the vectors from other open loop poles to this pole, okay. That is what was there, plus sum of the angles made by the vectors from open loop zeros to this pole. In the example that we considered, there was only one open loop 0, so that is why we had only one term, okay. So, that is what happened here. Now, what do you think will be the angle of departure from minus p3? It will just be a negative of this angle, or you just subtract it from 360 degrees. Why? Because the two should add to 360, right, because these are two complex conjugate poles, and any root locus should be a mirror image about the real axis, right. So, the angle of departure from P3 would be equal to the negative of the angle of departure from, sorry, angle of departure from minus P3 will be the negative of the angle of departure from minus P2, right. So, that is another important point. So, this statement calculation you do it as homework. The angle of arrival at an open loop complex 0 is 180 degrees minus sum of the angles made by the vectors from other open loop zeros to this 0 plus sum of the angles made by the vectors from all open loop poles to this 0. Okay, it is very complementary, right. Now, it is pretty obvious how we get this once again from the angle condition, right. Okay. So, this step once again applies only if we have complex open loop poles and complex open loop zeros, otherwise it does not apply. Okay. So, I will stop here. We would start from this step, complete step 6 tomorrow, and then we will construct the entire root locus, maybe do another example, okay, which will make things clear to us. Fine? Okay. Thank you.